guys, my name is Saddam Leonardo Kap, and in this video, this lecture is gonna based on Kleppner and kolenkow book, and today our topic is Newton's law. Now you may ask, I think you already have familiar with this topic because in earlier days also, in our earlier classroom also, we actually deals with Newton's laws of motion and all this fascination thing about with this. We have already studied the Newton's three laws of motion, like Newton's first law, second and third, and we have also studied a little bit of momentum conservation and energy conservation. But still, in this theoretical advanced physics of classical mechanics, we're gonna still review those concepts but in a very different manner. Now our lecture is based on mainly focus on theoretical concepts of things, like we have to dip deeper in theoretical physics, okay, and theoretical aspects of some concepts. Now with this in mind, we need to now understand or ask more about the Newton's law, that what's the hidden information in Newton's law and what's it's missing, that Einstein, after 200 years of its establishment, said that this theory is of no use, it cannot lead us to deeper meaning of the hidden nature. Why is that, and how does he conquer it? So before look into that thing, we need to understand that what are the hidden features of Newton's law, or what was the mindset of Newton when he was actually working on the motion of some heavenly bodies or any body in the earth, and where does he derive those F is equal to ma idea, and how he came into the life that he discovered this differential calculus. So this is our goal, to study Newton's laws of motion in a very different point of view, and which is more based on theoretical version, and then you will later realize that, oh, this was the mistake and we should study like this. Then we can really ask the questions which is relevant. Maybe Einstein's equation is perhaps wrong, it doesn't show us the complete picture. So with this in mind, we begin our lecture. Maybe it will consist some parts, we cannot cover everything in chapter 2, but first of all, this chapter is gonna have some glimpse of the what is going on inside Newton's brain and all these things. So what we gonna learn in this chapter? First of all, that is important. First, we introduced ourselves. What is this? We have already done it. Newton mechanics and modern physics. Okay, Newton's laws, Newton's first law and inertial systems. Yes, we have to understand what is the meaning of first law and how it is linked with inertial systems. And this was the key to realize this special relativity. Okay, from here things is actually becoming modified. Now Newton's second law, force is equal to mass time acceleration, and we will understand more about this force, that is this more fundamental or something else. Newton's third law, this is the consequences of conservation of momentum. Now we will understand about fictitious force. What is this? Is this real force or some coordinate artifact? Now we will understand this situation, like in physics, in experiments, we always care about measuring some quantities. Now how do we measure it? Like how do we define time, length and mass, and how do we actually define system of units? We will understand the history, we will understand the modernization which takes place in those systems. Now we will understand more about dimensional algebra. It is more important because in some questions or in mathematical things, when we try to write some equations, or we trying to figure some theory, first of all we try to use this dimensional analysis, that okay, can we sketch some rough idea about some systems which is completely hidden. You want to have some kind of finite some rough idea, for an example like Planck length, Planck time, that what could be the lowest time period of this universe, which is came out to be minus 36 seconds and perhaps more, okay, approximated as 10 to the minus 36 second and so on. So how one can define those kind of things, and we always, you have probably heard of quantum gravity. So one can ask that at which length scale this quantum gravity works, or at which energy scale this quantum gravity can be defined. Okay, so these ideas can be easily drawn from this analysis of algebra of dimensional analysis. So to understand this is very important. Now we will understand that how to apply Newton's law, because when we have mechanism and we are really a theoretical physicist, now our mathematics must be strong, but we know how to solve linear equations and do understand little bit differential equations, how to solve them. But still, when it comes to physics, we really need to construct those equations, and that is the hard part, how to frame the equations which will actually describe our system and how the system will evolution. So framing those equations is much more important, and we will learn that with the help of concept of Newton's equation or Newton's laws of motion, we can easily figure out the equation of motion for any kind of system. That is very interesting. And then we have already talked about polar coordinates. Now we will analyze with that polar coordinates some different system which have more symmetrical, like it has symmetry, it has circular symmetry, maybe elliptical symmetry and so on, because it is important. Okay, so I think that is enough for this introductory part, or what we gonna cover in this chapter 2 and what is coming in this. Now, introduction. Why introduction is too much important, and I will read it, and perhaps you have to listen. You may think that, okay, what is this in there? Why shouldn't you give your summary? I could have given you the summary, but it is no use, okay, unless and until you are devoted your time to understand these things, and these will motivate you to really think out of the box. Okay, that's why I am doing it in this way. So I hope if you like it, please share it to your friends, and I will ask you a very nice favor, a very little favor, that please subscribe my channel. And my channel is really small, and if you think I am giving you something very good and my work is very nice, please feel free to write your comment in the comment box, and that's enough for now. Okay, let's start our goal. Our goal in this chapter to understand Newton's laws of motion. Newton's laws are simple to state that they are not mathematically complex. Yes, F is equal to ma is not mathematically complex, and we know A can be written as d2x over dt square. So in some sense, this equation is second order differential equation. Okay, this is second order differential equation, and we think that, okay, with this thing it is not too much more complicated. Okay, suppose if you have force is constant, we can easily find that what happens to any object if it has some constant force acting on it. Now it is good. So mathematically complex. So at first glance the task looks modest. Yeah, at first glance it is in a kind of thing, second order differential equation, how gonna solve it? But if you have some mathematics, you can solve it. Combined definitions, observation from nature. Now how he has derived this thing, before the time of before we had the time, people had to do physics intuitively. What is the meaning of intuitively? Means they used to observe things, like they stare at the sky and they think that, okay, sun is moving or earth is rotating about the sun, what are these planets and so on. If I throw some object, what happens to this object? They do little experiments and so on. So today's doing physics is completely way more different than that time. That time people used to do this kind of observations, and they have some little ideas, they do geometry and all sort of things. Okay, and from those things they derive that, yeah, maybe we can define these things like this and so on. Okay, and so Newton was also inspired with the work of Kepler, and he was inspired from Aristotle and all those Galileo and so on. So he knew everything about them. Okay, so then he formulated that, yeah, by observation he realized that this force has to be proportional to acceleration, it cannot be proportional to velocity. Okay, so it was some intuitive, and he never realized that there could be any concept of space-time. He said that space and time is maybe some kind of a giant clock for universe. Everywhere time is same. No matter if you are in this galaxy or if you go to some very great velocity, time must be same. As we think the time is time. If it is 2 o'clock, then it will be everywhere the time ticks. That is the thing. Event means that 1 second passes equally everywhere. But this ain't true. If you in black hole or some neutron stars or near the stars, the time is completely different. Or even if you are in Earth and you go to the ISS, means that International Space Station, the time will be have something different. Here the order of difference is kind of 10 to the minus 12 of seconds. Okay, so there is different ticking of 1 second. Got it? So but for Newton, it was absolutely no way of think that space and time could be different. Now Einstein defined that space is fabric of something and it can curve, it can be so on, but Newton never realized it. Newton never really gave any kind of definition. He never defined space and time. He just said that there is space because he has observed everywhere around us, and in our surrounding there is nothing like space and time, because intuitively. Okay, so Newton's presentation of his laws of motion in monumental Principia 1687 left some of these points unclear, like we don't know anything about them. However, his methods were so successful that it was not until 200 years later that the foundations of Newtonian mechanics were carefully examined, principally by Venus physicist Ernst Mach. After 200 years later, not Einstein, but some other physicist name is Ernst Mach. I think you may not have heard about him. Okay, Ernst Mach. He first put the flag into his equation that might be whatever Newton has told, he is not perfectly alright. Those equations were not perfectly alright, but no one has ever taken him seriously. Maybe Einstein have heard of him, but nobody knows yet, because he was not too much think about it. Whatever anyone is saying, he was just like, I love to hear my own voice. Okay, so he used to study, for Einstein, Newton was hero. Just like for us, Einstein was hero and so on. So just like it. Why should I care about Ernst Mach and so on? Just like that. Okay. So he examined him that Newton's equation is not probably the corrected one, but nobody has taken him seriously. Okay. Our treatment is very much in spirit of Mach, but in this book we will actually go on how this Mach has prescribed it, and how can we change this Newtonian version, and how this can be completely different in our situation. Actually what happens is that it is not Einstein. If you go to history of physics, you will find that Mach has really given the core, and the idea and Einstein's idea are actually parallel to each other. Okay, when it came to that Newton's equation are not the equation which is actually nature's driving equation. Now I am giving you something really out of the book. Now here quantum mechanics works very well, everybody knows, but the thing is that why quantum mechanics work? If I am testing with hydrogen atom, helium atom, it works. It's amazingly work fine. We'll get whatever we need it. But the observation of the problem with the explanation of probabilities, superposition principles, infinity world, like superposition principle act as if there are maybe infinite possibility of world that exists in some time and so on. So there are red flags into it, but quantum mechanics also works perfectly well, just like Newton equation works perfectly well to describe the system of describe the dynamics of system. But there are again physicists which actually raise question that quantum mechanics is not the perfect description of quantum world. We need more. So this was the Mach idea, maybe you will become next Einstein who can say that yeah, there is something, some glitch, and I can fix that glitch. It is not that you can tell that yeah, Newton equation is bad, but what could be the greatest explanation? Newton and Mach has given it. Einstein and Mach has given it, but can you give? So it's the greatest job to actually identify those glitches and give a proper explanation. Newton's laws of motion are by no means self-evident. According to Aristotle, the natural state of body is rest. Yeah, before Newton there was Aristotle. Bodies move only when a force is applied. Aristotelian mechanics was accepted for 200 years because it seemed intuitively correct. Yes, what I have said you earlier. Carefully reasoning from observations and great leap of imagination were needed to break out of this Aristotelian mold. You know, that's what greatest thing Mach and Einstein has done. Analyzing physical system from Newtonian point of view requires effort, but the payoff is handsome. Means that applying the Newtonian equation to solve the second order equation to analyze the dynamics of any system may be very tedious, to solve this differential equation, but it actually gives you whatever you need it. Just like in quantum mechanics, you require very hard, but it pays off handsomely. It can explain whatever going on in lithium, helium, and so on. Quantum field, you may ask that quantum mechanics is obsolete now. Quantum field theory is extension of quantum mechanics. Okay, maybe something is little different interpretation, but the thing is the foundation is same. Foundation is quantum mechanics. So you can, if I am referring to quantum mechanics, so the thing is that quantum mechanics, quantum field theory, and everything is come under the same umbrella. Okay, analyzing physical systems from Newtonian point of view requires effort, but the payoff is handsome. To launch the effort, this chapter is devoted to presenting Newton's law and showing how to apply them to elementary problems. Now we will look for elementary problem. We are not going to solve like what happens to this big complex system. No, not our job. We are physicists. In addition to deepening our understanding of dynamics, there is an immediate reward for these exercises: the power to analyze physical phenomena that at first sight might seem incomprehensible. What is the meaning of it? Means that if we are theoretical physicists, we need to understand how to examine some systems using how to organize or formulate the concept and make a perfect or good mathematical structure, and then we need to solve it. And without solving it, can we analyze or can we think about those systems or not? So that is our job. That is our really job. Now if you want to become a very good theoretical physicist, you need this. Okay, without it you are incomplete. So only idea can't help you. You need to also formulate those ideas. This is the way things are actually working. There are alternative approaches to Newtonian formulation of mechanics. Okay, now here is very interesting thing. Newton's equation F is equal to ma is not the end game. First of all, there are so many alternatives to describe F is equal to ma also. These alternatives are Lagrangian and Hamilton. So you can actually derive F is equal to ma, which actually giving you the dynamics of any system, but you can construct it with other formulation like Lagrangian and Hamiltonian, in which the formulation is based on the energy. Here in Newton theory, that if you have some object, it can only move if you define what kind of forces is acting on it. But in Lagrangian and Hamiltonian formulation, they are actually saying that we don't need any forces. If we can define the energy of the system, it is we can figure out that what kind of forces is acting on it. Got it? So in more sense, force is not a fundamental concept, but energy is. For an example, what does it mean? Suppose in the system of so many molecules, so many gas molecules are there, or another molecules, they are hitting with each other. So they have kinetic energy, and maybe there are some kind of bizarre interaction going on. Now, if you are starting from Newton's law, then you have to write forces, like what are the sum of forces. Now, if there are n number of particles and there are really I is equal to 1 to n, and this n is so much bigger, now with this having mass m, what is this mass m, again they are pulling each other or attracting each other, what kind of interaction is going on, you are nowhere, you will never, it is impossible to construct or you can analyze the system using this force concept, because you know what kind of force. You have to first assume that this force have this property. No, you cannot. But with the help of Lagrangian formula, Hamiltonian, you may say that okay, these guys are moving with the energy, kinetic energy, and maybe they have some kind of interaction which will act as potential energy. Now maybe we can say that this potential energy will actually decay as 1 over r, maybe 1 over r to the power 8. Okay, maybe it is having r to the power squared. So with this kind of little assumption, we can easily consider that what kind of forces are actually acting in this system. So you don't, with this Lagrangian and Hamiltonian formulation, we don't need to guess what is the force is actually acting on those molecules. You don't even need to start, we don't even need to write this n particles of forces. And with this formulation, you can go deeper in the system, that there may be some symmetry. Now F is equal to ma, it doesn't talk about any kind of symmetry in the system. But Lagrangian Hamiltonian, from those you can actually go deeper and deeper and deeper. You can analyze some symmetry of the system, how they will evolve, what are the conserved quantities, and so on. So there are plenty of things you can do with Lagrangian and Hamiltonian, and which is completely absent. I am saying it is completely absent in force formula. So I hope I have successfully given you a greater detail to actually look into the force concept of Newtonian physics, that this is not an end game and it has very limited scope to actually understand so many things, and there are much alternative to this, and why Newtonian physics is, has needed to limit it, and how actually these assumptions are completely non-examined and they are on the base of intuitive idea. So you see, Newtonian mechanics has limitations and all these things. Now Newtonian mechanics and modern physics. I hope you are with me and you are enjoying the lecture. A word about the validity of Newtonian mechanics. Possibly you have had some contact with modern physics. The developments early in the last century of Einstein's theory of relativity and quantum mechanics. If so, you know that there are important areas of physics where Newtonian mechanics fails while relativity and quantum mechanics succeeded. Yes, I have already told you about relativity and quantum mechanics, and you may probably understand some of it. Briefly, Newtonian mechanics breaks down for system involved moving with speed comparable to speed of light. So Newtonian equation can't define if you have velocity very much near to 10 to the power 8 meters per second. It can't. And also for the system of atomic dimensions, which means that if you have the size of 10 to the power minus 9 or 10 meters, Newtonian equations can't define those things. The failure arises because of limitations to classical concept of space-time and nature of measurement. I have already told you that space-time is not same as you are actually realizing intuitively. It has the deeper meaning, and yet after Einstein and so many great scientists, we are still unclear about the concept of space and time. Maybe you are the next who can understand it. So take it deeply, that what you are going to understand. As you dig deeper into physics, you will learn the boundaries of Newtonian mechanics. Nevertheless, keep in mind that when Newtonian mechanics is valid, it is sternly successful. Now, for an example that where it is valid, if it has so many limitations, yeah, we will actually launching a rocket in the orbit of Saturn or in the orbit of something in our orbit of our planet using this Newtonian mechanics, because to solve the Einstein equation is completely hard and we cannot do it. We are using Newtonian equation to do that. Okay, so the Mars mission or moon mission is actually they are dependent on Newtonian mechanics, so it is completely way more successful. And actually, there's if you write down the Newton Einstein equation like G mu nu is equal to T mu nu, okay, the Einstein field equation, if you will taking the limit that where the gravity is not strong, it actually boils down to Newton equation like F is equal to ma. Got it? So it is not a very so that is the greatest thing about Newtonian mechanics, that if it is intuitively correct, then it has to be correct. Okay, and whatever the theory which actually surpass Newtonian mechanics, it has to be boils down to Newtonian equation if it is applying intuitively. Otherwise your development is completely wrong, and Einstein's equation does the amazing job to do that. Okay, so that's why it is saying that Newtonian mechanics is completely amazingly stunning to do that. The term Newtonian mechanics and classical mechanics are oftenly interchangeably. Okay, it is and now we are coming to more bookish part where things are like I hate names in a Feynman language. That I don't know what is the name of such and so equation, but I know what it is. My father taught me that you don't need to name of something and such and so, but you have to carefully understand what such and such have the properties it's doing, how it is, so on and so on. So maybe you have probably heard of this quotes. So that is the thing. But if you are doing physics, he has told that you have to have some familiarity of the words, otherwise you will be dumb enough that you know everything but you cannot open your mouth. And if you open your mouth, that what you are saying, people are gonna laugh at you that you are a physicist and you don't know this name, huh? Okay, except classical physics is taken to include Maxwell's theory of electromagnetism. The term, Newtonian mechanics, we are calling about that we are studying mechanism system, but classical physics is actually taking care of, classical mechanics having Newtonian mechanics as well as Maxwell's electrodynamics. So yeah, in my channel, also I am covering this electrodynamics lecture from Griffiths. If you are really interested, you can go and check. Those lectures are in Hindi, so if you know Hindi, then you can easily understand. Okay, I will later on also prepare lectures on Maxwell's equation in Hindi. So for that moment I'm that you could not find on my channel something in Hindi, something in English, but keep it with me. Okay, I will. This physics is really interesting, so I have to cover for both of the audience. Okay, yeah. The term modern physics typically describe development in physics after relativity and quantum mechanics appeared on the scene. The natural impulse might be to ignore Newtonian physics and proceed directly to modern physics. Yeah, you can say that. This would be serious error, because in major areas of natural world, Newtonian physics works brilliantly, while modern physics are of little use. For an example, attempting to describe planetary motion using the language of quantum mechanics would lead to quagmire of impenetrable equations. You cannot solve those things. Analyzing a game of billiards according to the rule of special relativity would quickly lead back to Newtonian equation as excellent approximation. I have told you already. So rather than make a blanket statement about whether Newtonian physics is right or wrong, we recognize that Newtonian mechanics is exceptionally useful in many areas of physics, but is inappropriate in other areas. Newtonian physics enable us to predict eclipse centuries in advance, but it is inadequate for predicting the motion of electrons in the atoms. In any case, because classical physics explains so many everyday phenomena, and because many of its fundamental concepts, such as momentum, energy, and conservation laws, lies at the heart of more advanced formulation, it is an essential tool for all practicing scientists and engineers. Now we came to the section 2.3, where we are going to analyze what is Newtonian equation. Okay, so let's start. Newton's laws are based on series of definitions and observations, and it is important to understand just which is which. In discussing the laws, we must also learn how to apply them. Okay, not only because this is the bread and butter of physics, but also because this is the only way to obtain a deep understanding of underlying concepts. We start by appealing directly to experiment. Unfortunately, simple mechanical experiments can be difficult to carry out because motion in our everyday surroundings is complicated by forces such as gravity and friction. Suppose I am telling you that, okay, do this experiment in your home. Suppose if you are applying some force F, and you predict that using the equation of motion, how far it will take time to stop it. Now you may ask that after t is equal to 5 seconds, and this block will stop after traveling of 5 meters, but you may wrong. Okay, if you will giving some forces for let's say 50 meters per second squared, you may wrong, because here if you are taking this object in some kind of surface, there is a friction force in it. There is some electromagnetic force. Friction force is actually because of some electromagnetic forces, because in surfaces, if you will zoom in, you will see that the interaction between electrons, you will never see that. Actually, you will see that there are some pretty kind of holes and all these things and some irregularities. We are calling these irregularities the friction force. So because of this friction force, you have to take into account this friction force and your prediction may be wrong. Therefore, we have to again do this experiment very carefully, and we have to invent some really brainstorming things. So these problems are very brainstorming. Then how you do those kind of experiments where you filter these other forces. Okay, so that's why it is important. To see the physical essentials, we would like to eliminate all disturbances and examine very simple systems. One way to eliminate the effect of gravity and friction would be to construct a space station laboratory, because in the environment of free falling space, most of the everyday disturbances are negligible. But if you want to do some experiment here or for class projects, it is not really feasible task to go to ISS, do experiment and then return to the Tesla rocket. It is not. So SpaceX, it cost billions of dollars. However, lacking the resources to put ourselves in orbit, we settle for second best, a device known as linear air track. We need to again experiment that whatever Aristotle or Newton has said about, or Galileo has said about the equation of motion or the laws of motion, is it actually true or not? Which approximates ideal conditions, but only in one dimension. Okay, we need to track it in one dimension. That okay, if anybody is in rest, will it actually is in rest? Or if anybody is in motion, then it needs force to actually because they will always be in motion. We need to do it experimentally, but in real life situation we cannot, because there are other forces that may stop it. How to do it? We are going to invent a linear air track. So linear air track is kind of this kind of situation you have, where what happens, we want to separate this is a very iron bar, and here is again this one is iron bar. There is a lot of friction. How to reduce it? So here there is a holes in it, and inside of it there is water. Okay, now you have to heat the water and there is steam going on. So this steam will actually counterbalance the mass of it. Now when it counterbalance the mass of it, then it will float in the steam. Now if you push it, it will actually running onto the steam. Now if it is running onto the steam, it means that the friction is very, very much negligible, because it is on a gas and you are running in the gas. It means that you have less obstacle. Now it is designed in such a way that if it is moving in this way, then it actually having some air resistance. We are calling it viscous force. So because of this kind of geometry, it doesn't face too much hurdle from this air resistance. Therefore this is the way we have designed it. Okay, now if you may have designed it like some point particle, then obviously a point particle will face very less resistive force, but we cannot do it because we know we need to have something to land on it. Therefore we have adopted this kind of structure. Okay, and now we have leveled it that it has to be perfectly horizontal, means that it has to be perfectly 180 degrees. So yeah, it is a very pretty tough engineering thing that you have to invent this kind of thing. Okay, so that's why we are saying that to verify those equations, it is completely hard, very hard. It's a very brainstorming process. The linear air track is a hollow triangular beam, and so I have given you the thing. Okay, and now you can use it, so I am not going to do it. Okay, now Newton's first law and inertial system. In describing the air track experiment, we glossed over fundamental issue. Motion has meaning only when measured with respect to particular coordinate system. Now you may already have understood that motion is a very relative kind of thing. That if you are in motion, how do we know it? You need to have some perfectly oriented coordinate system. Means someone is there, someone is running there, then you said, oh, you are actually running. And maybe if he is looking at you, then he said that, okay, you are actually going there, but actually the thing is that you are in rest and he is actually going. So this happens if you are in the bus, something is passing away. So yeah, motion is pretty much relative thing. Thus, to describe motion, it is essential to specify a coordinate system. For motion along the air track, we implicitly use a coordinate system fixed to air track. Means that the air track was, this was the air track, isn't it? So this air track was used as that this is your fixed x-axis and this is your coordinate system. Okay, and with the help of this, because it is in stationary, so whatever the object is moving on, so we are saying that yeah, it is moving on because this is stationary. That is the point of view to measure any motion. Okay, however, we are free to choose any coordinate system we please, including systems that are moving with respect to track. In coordinate system moving uniformly with respect to track, the undisturbed rider again moves with constant speed, though a speed different from one fixed to the track. Such coordinate systems are called inertial system. What is the meaning of inertial system? Suppose there is a system which is fixed and there are other coordinate system which is actually moving on, but it has velocity, some constant velocity like 2 meters per second. Some coordinate system is again moving, or something is moving again with maybe 30 meters per second, but the acceleration is pretty much 0. We are calling such system is called inertial systems. Okay, that it has the velocity 0, it has velocity 2 meters per second, they have different velocity, but the force on it is 0. Okay, if the force on it is 0, there is no acceleration. We are calling it the inertial systems. So not all coordinate systems are inertial. For instance, if you viewed from coordinate system, this is accelerating with respect to air track, the speed of rider would appear to change in time. However, it is always possible to find a coordinate system in which isolated bodies move uniformly. Yeah, so it is, if we are living in Earth, we cannot say that Earth is our inertial system, because Earth is still rotating, and if something is rotating, it keeps on because velocity is always changing, and if velocity is changing means it is accelerating. So if it is accelerating, it is no longer an inertial system, and if it is not inertial system, then we are calling it as non-inertial body. So this is the essence of Newton's first law of motion. The law is often stated in as word: a uniformly moving body continues to move uniformly unless acted on by a force. But the underlying concept is really the idea of isolated body, because all interactions decrease with distance as we take isolated to mean a body that has been removed so far from other bodies that interactions are negligible. A coordinate system can always be found in which the body moves uniformly. Got it? From this point of view, we can state Newton's first law as follows. Newton's first law of motion is the assertion that inertial system exists. So Newton's first law is telling you about an isolated body where there is no any force of interaction. Okay, because if there are other bodies and they are actually interacting with this body, if it is moved this way, and this will again move near to them. If you will not realize, but they will move because they will actually keep on forcing this way, and because of force of gravity, Actually, these forces of gravity are attractive in nature. So if it is moved 5 centimeters, they will also move some centimeters. So therefore, this is body for the isolated one, that you keep them very far. We cannot, these motions are not affected. So what you have to do is that keep this isolated body, do it somewhere else. And what you can say that if any isolated body is moving, or some body is moving to them uniformly, we are saying that some inertial system is exist. So Newton's first law is assertion of existence of inertial systems. So Newton's first law is part definition and part experimental fact. So it is not completely very theoretical, it is the experimental fact, and we have defined something. Isolated bodies move uniformly in inertial system by virtue of the definition of inertial systems. We have said that there is no any acceleration, there is no any force, so it is mainly as a perfectly isolated body. Got it? Okay, in contrast, the assertion that inertial system exists is a statement about physical world. Newton's first law raises a number of questions, such as what we really mean by isolated body, but we defer these for the present. So again, whenever we try to define something in theoretical point of view, we have to give a very concrete thing, that what is the meaning of isolated body and so on, how you are going to isolate something. We will understand it deeper in another chapter, okay? Not this. We cannot mix all these things in one thing. So I think we will cover the Newton's second law later on, and we stop here. Then if you have really liked it, please give us thumbs up, like our video, and give us a proper comment and share to your friends. Thank you so much for being here.